Yeah. So this meeting is being recorded. So, okay. So today's topic, I won't get like much time. Within like an hour or so, we should be done introducing this. We don't have much to cover. Most of the material, for example, when it comes to implementation, we'll be working through it either through the practice problems or office hours, or people can reach out to me and then I can get people up to speed. But this one is just to make you know, like after this, what do you expect to see if you're out there like looking for information or studying for binary trees or some coding questions which might involve anything to do with binary trees. Okay. So like what's a binary tree? So let's see. Okay. So so a binary tree, it can be empty. Okay. Yeah, like if there's nothing, it can be empty, or it can have like some kind of root node. Okay. Uh and if it has like the root node, uh you can also have like some kind of you can have some left and like right binary like yeah subtrays can root node and can have left and right uh trees, yeah, from the root node. So the trees or the subtrees, okay, the subtrees are trees themselves. If you remember from our CS7, when we had a function which had to define if a branch is actually a tree. So yeah, you can think of this as like, the left and right subtrees. You can think of this as like the branches. Okay. Yep. So uh, so binary trees most like, when we look at them, usually we investigate them using like binary search trees. That's what interviewers they ask the most. So you can just say BST. Okay. Okay. So yeah. Um, if like for example, let's give like some kind of a representation. Let me use a different color here. Okay. What if we have like some graphical representation? Okay. What does like a tree look like? So you can have maybe let's say you have a node here. Okay. And then there's another node. Yeah. No, a node B. And then you have another node there. And then it kind of like, it kind of stretches. Just like having different, having different nodes. You can have maybe another one there, then maybe have another one. Okay. And then you can also have a, so let me complete this structure and then I'll just fan it out. And then you can have maybe another one here, another one. Maybe let's make these ones balance a little bit. Okay. from this one, how can I make it interesting? Have another one there. And then have this one, let them be at the same level, but then also like increase this one. Okay. So, okay, and then let me cut this out because I want to, I want to make it smaller. Okay, yeah. So, yeah. So this is our tree. So let me choose a different color, maybe green. Okay. So let's say this was node B, and then this is A. B, and then we have C, D, E, F, G, H, we have I, J, K, L, M, N, O, P. Okay. So this is, just some random, binary, like, yes, tree. So let's say inside the nodes here, you can actually store information. You can store data. For example, if we decide to store maybe like integers on this one, maybe you can like have maybe like a number 314, you can have 6, you can have 6. So basically you can have some number, some information can be stored in here. This is like a binary tree. So we say that what's at this position here, that's depth 0. And then on this level, that's depth 1. And then these ones, that's depth 2. And then this depth 3. And then this is depth 4. Yeah, depth 4. And then this is depth 5. So let me just choose this coloring. So basically this is depth 0. These nodes are at depth 1. And then these ones, they're depth 2. And let me choose another. And then these ones, they're depth 3. And then this one's depth 4. And then maybe the last one is depth 5. Okay, so that's the other terminology which you just use. So basically like this, that's how a tree looks like. So from this idea, like there are just so many interesting problems which you can solve, in computer science, either searching or storing information. And this idea of also asymptotic analysis really blends well, when you start thinking of like, how can we search? Maybe can we also search one half and like discard the other? Or how can we optimize this? So even like understanding that, as you go down, like there's a depth, and then there's this is we know that this is the root node. This is the root node. So let me label it maybe here, like root node. Okay. So that's the root node. And then, this is the left. This is the left branch. And then this is also at the right branch. But then we also know that by the abstraction, of the tree, they're also branches. So the logic just extends. And then at the end, at the bottom, we just have, these nodes which don't have, for example, these are leaf nodes. So the leaf nodes are nodes which don't have children. So these ones at the end. Okay. So the left sub branch, the left of a leaf node is empty, and the right of a leaf node is also empty. And then sometimes you might find some other nodes. For example, this one, it has a right, but then it doesn't have a left. The left is empty. So that's why, like, we said, like, since this idea that this has two children, but if one of them is empty, that's why we had this idea that, okay, it can be empty. For more formally. Okay. Questions. Okay.
Yeah, I have a question.
Yeah.
Let's say we want to like have an algorithm that goes like an algorithm that actually like I want to know like more about like the like using depth search algorithm like in order traversal,
Okay.
pre-order traversal, and in the other algorithm like with the binary search, and then also like how to like let's say I think the question I had, I'm not finding the question, but the question was like doing an in order traversal, and then like we were supposed to get like the last like to get the we're supposed to write to return like a reverse of the binary list of the binary tree, but using in order traversal where you're now listing it from the left nodes, the right nodes, and then the node, and then you go again as long as there is a node. Like I'm not finding the question.
Oh, okay. So yeah, I will go on like and introduce like the tree traversals. Like right after this. And then so like there's like death first stage, and like so many other ones, like in order, post order, pre-order. So we just like touch on them like as a whole. We might not like dive deep into how each and every one of them actually like works in the interest of time. But we'll just like go through them, and then for more questions we can like attempt them more on like hospitals. But yeah, it's a good thing you're actually like you've already started like going down this path. Okay. So yeah, in like just a few minutes we'll get to your question, like on traversal. That's the main interesting part about these binary trees. Okay. So yep. Okay. So there are some things, for example, which I wanted to highlight from this tree, so that if you are answering questions and then if they ask, some other things, yeah, you basically know. Okay. So let's say you want to so like for example, I've said that like each node basically accept the root is itself, either a left subtree or a right subtree. Okay. Uh, so if if for example, like B, in this case B is a root of this left subtree. Okay. So this is a subtree. This is the left subtree in relation to this root node A. So we say that B is the left child of what? Of A. Okay. Yeah. Okay. B is a left child of A. Okay. Yep. So let me just. Okay. And we always say that A is what? A is a parent of B. Okay. So you should note that with the exception, for example, of the root, every node has a unique parent. like, each and every other node should have a parent. Yeah, if it's a tree, except the root, because that's, like, yeah, that's the root. So because of this, like property that each node should have a parent, basically, like, you can trace a path from the root, yeah, to any node. For example, if you want to go to M, okay, we know that if you want to go to M, you can basically trace a path. How do you go to M? So you start from A, then you come here. Okay, so we call that, and let me use a different color. So we call this the search path. Okay, so the search path is, you can basically like follow along, like a sequence of nodes to go to your desired one. Okay, so that's the search path. Okay, so there are different ways, for example, like where you can like move along, maybe from one node to another, like you're searching for it. But as long as you just have a sequence of nodes where you start from one, and then you start from the root, and then you go to your desired node, what you get is what you get, a path, because you're actually searching for that node. So yeah, we refer to that as the search path. Okay, so if we also look at A and B, we have this kind of parent-child relationship. So if we now like extend it, for example, we know that I is the right child of A. Okay, but what's M? So we know that, okay, M is the right child of L, and we can basically have a parent to child relationship to this one also. So now we can now also have some other terminology, like, what's an ancestor? Okay. So defining an ancestor, we say that a node is an ancestor of maybe like, let's say another node is an ancestor of, let me use M as an example. It's an ancestor of node M if, okay, so how did we, like, for example, know that, okay, M was, like, we can basically trace the parent to child relationship from M all the way to A. So all of these other nodes, L, K, J, I, A, then ancestor. Why are they an ancestor? Because if this node, if it lies on the search path from the root to node M. Okay, so to make it like arbitrary, let me just yeah, put maybe like a variable like X. Okay, so a node is an ancestor of node X if it lies on the search path from the root to the node X. So you just randomly pick, which of your node will be X, and then now you find that search path, this path which goes, to your X. In this case, our X is this node M. So any node which lies on the search path is what, yeah, is an ancestor, yeah, of that node. Okay, so if we have an ancestor, we can also define, what what a descendant. Okay, So a descendant, like if let's say a node, okay, so is if a node is an ancestor of node, yeah, in this case, let's just say node y, okay, and then we say like node y is a descendant of that node. So these are like, at least so an interviewer might just ask you about like the ancestor or about the descendant, so or the search path. So they have this terminology, which if you know the terminology, if it makes like asking for clarifications or approaching the problem, yeah, quite easier. Okay, and then yeah, so we also like we saw, for example, the depth, like for example, like depth whatever up to depth 5, 1, 2, 3, 4, 5, yeah 6. Okay, so if we look at the depth of yeah, okay, the depth of a node, okay, of a node X, okay, so what's the depth of a node? The depth of a node, for example, if we look at node M, we say the depth was 5, okay, so what do we really like refer to by depth? So the depth of a node X, in this case, X representing our M, becomes the number, okay, of nodes on the what? On the search path, okay. This search path started from A, which was our root. So on the search path from the root, okay, to what? To node X. Yep. To node X, yeah, but not including the node X itself. Okay. Yeah. So like no, I'm just covering terminology and all, yeah, and stuff. Okay. Okay. So we have, like we have this depth. We have this depth. So you can, for example, to live from A to 4, to M, from A to M, what you get is like, it's depth 5. Okay. But if you are, how we define the depth, if you have, if you want to live from the root node to this one, basically the number, if you want to go to C, this search path goes from A to B to C. So the number of nodes from the root up to C, but not including C, is what? It's 1, 2. Okay, so then C is what? It's a depth what? It's a depth 2. So now it brings about another interesting thing which you also have to define. So we also define the height of a tree. So the height of a binary tree, because we can like basically, if you go to D is a depth 3, but only M was a depth 5. So M gives us the height, the height of the tree. For example, if you just have any tree and we say like measure how like the height of this tree, basically you want to find that branch which stretches, which is the longest or something like that. So the height of a binary tree is the maximum depth, okay, of any node in that tree. Okay. Okay. Yeah, that's the height of a binary tree is the maximum depth of any node in that tree. And then what we can also get is it's like we just like we say like all per each level, all nodes which are at the same level, they have the same depth. So a level of a tree is all nodes at the same depth. Okay, so for example, for this green one, this green thing represents a level. So let me write it down. This represents a level. So all these nodes, they are at the same level. Therefore, they're at the same depth. Okay. Okay. And then we also describe like some binary trees in terms of like let me use now a different color. Okay. So we say a binary tree is full. Okay. A full binary tree. Okay. What's a full binary tree? So every node other than the leaves has what? Has two children. Every node in that tree other than the leaves has two children. So let me, because that's the key thing. Okay. For example, if you have your tree like this, okay. So in this case, every node has two children except for the what? For the leaves. So let me highlight because other than the leaves has two children. So it means it's full. It's full. Like full. Yeah. So that's one thing which we okay. Yeah, that's one thing which we also like define there. Then we also have with okay, so let me see. Okay, let me expand this one so that the next example will make more sense. Okay, so I can remove this. Okay, yeah, this is an example of a binary tree, which is full because this is also a leaf node. Okay, and then now we have a perfect okay. Perfect binary tree. So a perfect binary tree is basically a full binary tree. Okay. So it's a full binary tree in which, okay, So I wanted to use this, this example. So like the example which I had before, where if you kind of look at every level, so in which every, in which every level is completely filled, every level except the leaf node, except the leaf node. Okay, in which every level except the leaf nodes is what is completely filled. Completely filled. Okay, and all nodes are as far left. This is not just redundant, but like, you're filling them from like far left and all far left as possible. Okay. Okay. Yeah. So yeah, that's a perfect. And then we have a complete binary tree. Complete binary tree. Actually, yeah. Yeah, wait, basically like, so a perfect binary tree, whatever I said here. So it's a full binary tree in which like all leaves are at the same depth, except, okay, so, okay, I'll just take this. I'll take this and put this here. Yeah. I mixed the, okay. So the perfect binary tree then, to make it like less complicated, let me just say all leaves, are at the same depth. For example, if you take this paste, and then if we add 2 more leaves, then we look at them, then we can see that, leaves, they're what, at same depth. So they're at the same level. Now we're just, this same depth, same level implies same depth from like following, this part. A level of a tree is almost at the same depth. So this level, since all of them, they're at the same depth, then it just makes it perfect. And then, yeah, the complete, the complete binary tree. Yeah, basically it's a full binary tree in which every level is completely filled, So by completely filled, we mean even like in terms of the data which is stored inside these like single nodes. So a complete tree to be perfect, and also it's a full tree, but then the information inside is also filled. Okay. So now let's like get to like how asymptotic analysis would play in this. So this, like, for example, like this terminology, for example, which I'm introducing, like a perfect tree and a complete tree, you can basically kind of think of them. Yeah, you can think of them as loosely the same, because they if you look at even at the definition, they just like imply each other, and they really like ask you to distinguish between a perfect binary tree and a complete, because usually like perfection, completion, or perfection can like imply the other. Okay, and then so now if we look at this if we look at this binary tree, uh the type of mathematics which now gets involved in here is you can do proofs by induction. You can like we can like look at the height, and we can look at the nodes, and basically there are some things which you can like understand from just this structure. So let's see how we can understand this issue, for example, when they talk about space-time complexity, or like all of these things, and then it becomes it will get simpler for us now when we're like solving problems or understanding the terminology of trees. Okay, so okay, so there's so some properties, some properties which we should just like throw out there. Okay, so any questions? Let me look at the chat. Okay, no questions. So if you have a question, you can even like unmute and ask a question, and then I'm okay with any of that.
Can you come again with the definitions, the height and the level of the banana tree?
Okay. So let me use this example. Okay. So if you look at this, we had like you see like there's this color, this red, like this represents a level. A level has the same depth. Basically, we're saying all the nodes, the root node is at depth 0. Okay, but then we're like all these nodes which share the same depth, basically they are at the same level. Okay, at the same level. So if you now want to find the depth of a node, basically we say it is the number of nodes from the root, like to itself, including the root but excluding that node. For example, the depth of node C is 2, because you count this node and this one. But then if we check the depth of all the leaf nodes, a leaf node is not a node which has no children. For example, the depth D is at depth 3, E is at depth 3, H is at depth 4, M is at depth 5, N is at depth 4, P is at depth 3. And then if we ask you, what's the height of this tree? Basically, you take the max of these different depths. In this case, the height will be what? Will be depth 5. So, and then we also say that by locating any node, let's say a node X, searching from the root to that node, what you get is what you get a search path. Okay, so any node which lies on that search path using the parent to child relationship. We said like B is a child of A is a parent of B, A is also a parent of I. So any node which lies on that search path, it also defines an ancestor and a descendant. Then the other term which we described was like, a tree can be like can be full, that is like every node other than the leaves, has two children. Okay, in this case. But then now this one is full. But now if we want to actually look at it as like, perfect, the ideal one or the complete one, it's this case where all the leaves are at the same depth. By all the leaves being at the same depth, basically like, you imply that every level, is completely filled and all the nodes are like as far left as possible. They are basically like something like that. So yeah, this is like our ideal case if we're searching. And we can see like later that solving a sparse, if this is complete, or if it's or if it's not as complete, for example, as you'd want, it also affects the runtime like different ways. Because using this logic, you can basically think of a list. You can represent the elements in a list in a tree-like structure where you have the root, then you have the left child. Okay, so you have the root node, then you have the left child, then you have another one, 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 and all. So now if you have this, this is a tree, but then because this tree, it's not, doesn't have that balance, doesn't have, complete. So now if you're like, for example, you want to like search through it, you know that if you are searching through a node, basically it will take you of n time to search through it. Already it destroys, some of the properties which we would want to observe from searching through, maybe if it's a binary search tree where you can like discard half of the elements, and also we'll see that as I bombard you with problems. But yeah, that was a good ask. That was a good ask. Okay, so I want to introduce you guys, to this, to some properties. So okay, so the number. Okay, so this, this. Okay, so this affects, things which you see. So the number of leaf nodes in a full binary tree is one less. No, like it's the number of is one more. Okay, let me say one more. Is one more than the number of non-leaf nodes. Okay, for example, in this case, this is a full binary tree. How many leaves are there? There are 4. How many nodes are not leaves? There are 3. So there's always this difference of 1. This is also like full. Also like, so how many leaves? There are 3. and then the other ones which are not leaves, there are 2. So that's other property of this 4 binary tree. So now it makes, now things start getting interesting. Okay, so if you need proof, you can basically prove you can prove this using or by induction. Yeah, you can prove this by induction, for example, like either I think if people might be familiar with proof by induction, it's basically like that's where we derive recursion also from, like, proving things by induction. So yeah, you can prove this theory. So take this as a theory or effect or a lemma. Okay. Okay. And then which other property do we have? So a perfect, binary tree. Perfect, you can just say perfect or complete. Okay. Perfect or complete binary tree. Okay. For example, this one. This was an example of a perfect or complete binary tree. Okay. So a perfect binary tree. Okay, let's say the height in this case, let's say this height was 2. Okay, a perfect binary tree of height h, okay, contains, okay, so exactly 2 to the power h plus 1 minus what? 1 not. For example, if h, let's give like an example. Okay. For example, if h is equal to 2, then we know that the number of nodes, is what? Is 2 to the power 2 plus 1 minus 1. That's what? 2 to the power 3. What's 2 to the power 3? Minus 1. That's what? 7. Okay. And, by 7, then we know that if we look at this number of nodes, that's 1, 2, 3, 4, 5, 6, 7. Okay. So if we also look at this, we can also see that the number of leaves, it was actually like, it's 4. And what's 4? 4 is 2 to the power h. So we can expand this. So a perfect binary tree of height h contains exactly 2 to the power h plus 1 minus 1 nodes. That's the number of nodes, of which 2 to the power h of those nodes are leaves. Okay. So if, for example, now we say if h is equal to 3, okay, then we know that the number of nodes is equal to what? 2 to the power 4 minus 1. That's what? 2 to the power 4 minus 1. Okay, I see there's a question on the chat. Oh, 5 minute. Oh, okay. 5 minute break. Yes. Let me finish this, and then like we'll take a 5 minute break, and then we'll come back. Okay. So for this case, it's 16. We get 15 of these, but then the number of leaves is equal to what? 2 to the power 3 is equal to 8. So basically, if we're to draw our tree, we can even start by drawing the leaves. 2, 3, 4, 5, 6, 7, 8. And then we connect these ones. No, because they're like, but we know that if we connect, we have to use, so these are 8, then these are 7. So which means we're left with what? With connecting 3 of them, of these ones. And then yeah, so basically, like if we look at this, these are what? The leaves, that's 8, and then the other ones, they're just like what? 7. So that's a property of of a binary tree. And then the last thing is no complete or perfect binary tree, which has n nodes. Okay, has height log n. Okay, yeah, that's yeah, that's it. So yeah, and then we'll take. Actually, I think we can take a break, or we can call it, yeah, a day, depending on. I feel like I've just been going like more technical, like, and more mathematical. So yeah, what do people say?
Yeah, I think we can take a break. If there's more you wanted to cover, I think we can continue. Yeah, today, just after a short break.
Yeah, I also want to learn about the traversal thing. So
Yeah.
if you want to continue, it'll be nice.
Oh, okay. Oh yeah, so uh, we can take a short break, and so we'll continue at what? At in 5 minutes, a short 5 minute break. If you have other questions, you can ask me questions on the chat. I'll be watching, and I also need to charge this thing. But yeah. Okay. Okay. So why do we say that the height? The height is log n. So basically, if you look at this, we say it or 2 to the h. Okay, let me make this more visible. Let me use a different color. 2 to the h. Yeah, h plus 1. Okay. So we say like 2 to the h. That gives us the leaf nodes. Okay. Binary tree of node. Yes. Okay. Yeah. Okay. So we said a binary tree contains these 2 to the power h plus 1, minus 1 nodes. Okay, so we said if these nodes, for example, in this case, if we have n nodes, what's the relation between the number of nodes and the height? So we said that 2 to the power h plus 1 minus 1. That gives us, the number of nodes. So, you guys, you can basically do your math right here. You can like 2 to the power h plus 1 is equal to n plus 1. And then you can take the log log base 2 Okay, now let me I'll solve this like a math teacher. And then you take the log of base 2 of 2 to the power h plus 1 on both sides, log base 2 of n plus 1. And then if you solve this one, you basically get that h plus 1, it's equal to what? Log of 2 to base 2 of what? Of n plus 1. And then you get that h is equal to log of base 2 of n plus 1, minus 1. So in terms of now looking in terms of like of log, when we're like, when I was introducing like earlier, the base really doesn't matter much. So you can, you can just say, this is, since the base doesn't matter, you can just say log. But, adding a constant as n becomes big, as n approaches infinite or stuff, adding 1 here won't really make much of a difference. That's the same with subtracting 1. It won't make much of a difference. So that's why we say that, the height is what has height, which is like, like whatever, like log n or something. But this is like the actual like mathematical one, for example, if you want to calculate it. But then this is like, kind of gives like an approximation. So how in terms of using mathematics, it won't specifically be this, but they use these things. Maybe you've seen them, like which says like maybe like something like most it has to be you guys did calculus, what these things. So it's like either you're setting like a floor or a ceiling and stuff like that. So this sets the floor. Says at least it has to be but the more exact one, it's given by this formula, and then the other one just generalizes. This is how you find the height, because we just solved, we made form 3 mathematics or form 2 mathematics make h the subject of the formula, and then that's what we did. Okay, and then we also a tree can be left skewed. Okay, a left skewed tree, is you have no node has a right child, and then a right skewed tree no node has a left child. So in this case, so in either case, we just say like, the binary tree is skewed. It can be left skewed or or right skewed. In this case, for example, if it's left skewed, basically you're just turning it into like, some linked list. Yeah, it follows, like the pattern of a linked list, either like going this way, or in this case, going that way. So it would like 1 node and 1 node, 1 node, 1 node, no right child, and then this one, no left child, and it continues like that. Okay. So now if we look at some, the key computation. Okay. So we can, like, for example, let's say traversing all the nodes in a tree. Okay. So, sometimes like traversing, sometimes they call traversing, they can also call it like what? Or walking. Yeah. Let me just put a note here. Sometimes it's called walking. Okay. And then go back to my lovely color. Okay. So you can, okay. So when you traverse, there are like 3 ways, of traversing. You can traverse, like tree traversal. There's what? We have the pre-order, the in order, and the what? The post order. Okay. So let's look at what's the pre-order. I don't like this color. Let me choose another one. What the pre-order? So if you are traversing, if you are walking through, you always start at the root. Okay. So what happens is, like your function, it takes the root, but then what it does is it first visits, pre-order traversal. Step 1, is traverse the left subtree. Okay. And then step 2, then you now what? Visit the root. Okay. And then step 3, traverse the right subtree. Okay, wait, this one. Oh, this is oh, no. This is in order. But yeah, it confuses me. Okay. That's in order. So for pre-order, what we need is we first visit the root. Okay. So let me change this one. Yeah. Yeah. Okay. Yeah. Pre-order. So yeah, start with the root. So we visit the root, then we go to the left, and then we go to the right. Yes, pre-order. Okay, yeah. And then in order, what to start with, like the in order one is, we start with the, yeah, that's the one which I wrote before. Traverse the left subtree, and then visit the root, and then the third one is traverse the right subtree. So that's an in order traversal. And then the post order, I think now you know what the post order will be. The post order will be, the first one is traverse the left subtree, and then traverse the right subtree, and then 3 visit the root. Okay, so let's look at our tree here. Okay, so let me just look at, in the chat. Let's say, can we do an if we do yeah, just on a piece of paper, like I write on the chat, just do an in order or post order or pre-order traversal of this one. Okay, so let me do one with you guys, and then we can see. Okay, so if we do let me start with a pre-order traversal. What a pre-order says, we first start by visiting the root. So let me copy this tree, because yeah, I'll need to use it in the other part. What? Okay. No. Some of us were now very old. Technologies are very hard to use. Okay. Copy. Paste. Okay. So yeah, if we look at this one, let's say now I want to do an a pre-order. Okay, let me choose a different color. Okay, let's say I want to do a pre-order. Okay, so pre-order says I should what? I should visit the root first, and then traverse the left, and then traverse the right. So by visiting the root, I start with what? I start with A. So let's say I have a fringe, or I have something where I'm storing. Every time when I visit something, I add it to a list, visited. Okay, let me say, okay, visit. I don't like this color, it's just too bright. Okay, let me say visited. Okay. let's say if I visit A, and then it says, okay, so let me choose a different. Okay, if I visit A, and then it says I should visit the left of the tree. So this is the left and traverse it. So if I'm looking at this one, this is now a tree. Then it says, oh, I should traverse this one. So then I visit B. And then from B, it says I should also like traverse the left. So now I add C. No, and then I add what? I add D. But then after adding D, like if I look at this smaller one, C and D. So I visited the root, I visited the left, now I'm visiting the right. Okay, so that's why here we add what? We add E. Okay. And then now, oh, how did I even get to this one? Oh, I was looking at B, so I just visited B. I visited the root, so now I'm done visiting the left subtree of B. So now I have to visit what? The right subtree. So that's when, like, you know, when you now visit the right subtree, and then you get what? F. But then there's no left. If you look at this one, if you're here, you're supposed to visit the left, but then the left is no. So now you then go to what? G and H. G and H. Okay. But then, so you're done like exploring all this not here. But oh, this was left of what? Of A. So now you can then like start looking at now, because the algorithm says after visiting the root and traversing the left, then you should traverse the right. So we visited the root A. There we have A. Then we did a traversal recursively on, then we, by traversing the left branch, we're visiting all these other ones because we're calling on that same, you know, like algorithm. And then now we can then traverse the other one. So now if we do this, for example, if we traverse this one, we know we're going to visit I and then deal with this branch first and then now deal with the other one. So we can just like, you know, say we have I, and then we have what? J, then we have K, then we have L, okay? And then we have what? M, then we have what? N. But then we got what? To O and P. So basically how I named these things, no, I was just naming them from like this, you know, going in this order. But how I named these letters to start with, it was like, you know, a pre-order traversal. So, you know, this is just like how you, oh, letters in the alphabet and that order. A, B, C, D, F, G, okay. M, N, O, P, whatever. Okay. So now I did this one. So now you guys, you can basically like, you know, do the other ones and yeah, just see how we can, you know, for example, how we can get an in order. Okay. So an in order are visited. Okay. So what does in order say? In order says we traverse the left and then we visit the root and then we traverse the right. Okay. So let's look at that tree. How can we do it in order? So when we traverse the left, okay, so it says we started the root, but we don't visit the root. We have to first traverse this one. But when we traverse this, so an in order traversal will keep on going down the route, and then it first visits this leftmost route, without like any kids. So that's what another interesting property. Now you start by visiting, this one. Okay. Because of whatever, that logic. Because we first said, we have to first traverse to the left subtree. So when we're going to get D, but then after D, so it now has to visit what? The root. So you are now going to visit C, then it's going to traverse the right, then you're going to get what? E. Okay, so you just look at this simpler case. With just these three nodes, we know that we say it first has to visit the left, then visit the root, traverse the left, visit the root, traverse the right. Okay, so now when it was at B, the command was for it to first traverse the left, and then after that it then had to visit the root, and then what? Traverse the right. So that after finishing traversing this one, then it has to what? It has to visit B. Okay, and then now it can traverse the right. But when it traverses the right, for example, it will come to this one. So for this one, it says it has to visit the left, traverse the left, but the left is not there. So then the next thing is visit the root. So the root is what? It's F. And then you continue, to visit the right. But then when it visits the right, this one, okay, it traverses the right. But for traversing the right, this is take it as if it's it's one tree on its own. So the in order says it has to start by traversing the left and then visiting the root. So instead of G, we're first going to get what? To get H. And then we follow with what? With G. Okay. So now it has finished. We're finished traversing this part. Okay. So now then we can, this was the left of the root. Now we can then visit this root. Okay. So when we visit the root, we get what? We get A. And then from A, we now, like our algorithm, like it now says no. Now says traverse the right. Okay. So now this is the right. Okay. But then when it says traverse the right, we look at this tree. So if we look at this tree, basically it can't visit this root if it doesn't fully explore this path. So, and also, when it reaches like J, it will first need to explore what's on the left, but there's nothing on the left. So if it traverses the left of J, it knows that, okay, it has done. So it can now come back and visit J. Then after visiting J, now think of, you have this as your tree. It has traversed this one. Now it needs to traverse the right of this node, J. But by traversing the right of this node, you now have this tree, K, L, M, N. So it can't visit K because it first has to visit what? L. The left, this is the left. So in visiting the left for this one, before it visits L, it first has to visit this one, but this is empty. So after like traversing this empty one, it's going to now visit L. Okay, so after J, we're going to have L, then it then traverses the right, and then we have M. Okay, so after traversing this one, okay, this was the left of K. So before it goes to the right of K, we have to visit K. So we get K there. And then now we get what? Then can visit the right, we get N. Okay. But then we're like, okay, now we've finished traversing this left of I. Now we then go on to traverse what? I, to visit I. Okay, we visited I. And then now we then traverse the right of I, which is what? O. But before it gets to O, it has to first traverse the left, which is empty in this case. So that's what we get is we get, then it now goes, then it has to visit O. So when it visits O, you get O there. And then now it traverses this, okay. And then now it traverses what? P. And then you get what? Get P. So that's your order. So for interviewers, they might just give you a binary tree, maybe like this. Then they can say, oh, can you show, this order? What do you get, when you do an in-order traversal of this tree? That's a perfectly valid interview question, and they love asking that. They won't ask you implement almost the high stuff of implementing. They like, okay, do you understand the traversals? This is a more common question. Okay, so let's reorder.
Eric.
Yeah.
Just on my questions during the interview. So is there code for doing this, or I'll just have to draw a graph and show it like this?
Okay, so yeah, we're going to write write the code after this, for traversal. But it's very easy.
Just a follow-up question, like, so are they also like inbuilt functions like for traversals too, like to say there's like a Python library for these functions?
Oh, maybe someone out there created, like libraries. It might not be inbuilt, but it's can like import it if someone made it, or you can like write your own. Yeah, but mostly it's this one is like, mostly you write your own. For example, even like when you'll be doing depth first search, the A-star, Kruskal, Prince algorithm and all this, like understanding the algorithm and then like writing it from that. But you can, for example, like depending maybe on a course which you're taking, but for the interview, mostly implementing all of this from scratch sometimes, like, for example, if someone says implement the cyclic, whatever, double linked list, it just takes time. And also they can just ask you some part, they can say, or reverse the linked list. An interviewer can assume, okay, you already have a BST, define a function to traverse it. You see? So, but if you're practicing, it's good to know how to just write the full code of how you can implement it on your own. Start a new file, create the class for a binary tree, and have initialize the node, initialize all those things which are needed, and yeah. Okay. So I left with like 7 minutes. Let us do the post order one, because I'll be sharing this slide, like this PDF to the WhatsApp group. So I would like it to be beneficial if people can see. Okay. So if we look at the post order, so for post order it says traverse the left, traverse the right, then visit the root. This is the interesting one, because so when they say traverse the left, traverse the right, then we know automatically know that the last element is going to be what? To be A. Okay. Yes. So now how do we traverse? When it says traverse the left and then traverse the right and then visit the root. Okay, now we're traversing the left. So by traversing the left, this is the left, but this becomes like the root node of our left subtree. So now we have to traverse this one, then visit B. So basically we'll come to the simple case. So in this simple case, it says we have to traverse the left, that's like D, then traverse the right, that's E, and then visit the root, that's C. Okay. So, and then now we have to now traverse the right of this. So this is the left. Now we have to traverse the right of B. Okay. So always like use another node for reference. But how do you traverse? This is the right of B, but then this is the root of this tree. So it says you should traverse the left. It's empty. So like you don't have to do anything. Or traverse the right. So before you come in to visit F, now let's look at this, right? This is G and H, okay? So this is our root now. So we have to traverse the left. If we traverse the left, that's where we put what? We put H. Traverse the right, there's no right. So we now visit the root, we now visit what? G. Okay. So after that, because we're done like traversing the right, then we can also visit that root, what? F. Because we're done visiting the root F, we can now also go and visit what? The root B. Now we're fully done like a left traversal in respect to what? This node A. So now we have to then do a right traversal, and then we now visit what? A. So a right traversal, if we now look at this tree, okay? So if we look at this tree, this becomes like our root node I. So we first have to traverse this part and then traverse this part. And then from there, we can like now visit I. Okay. So now we already know that before A, like I will be like, for our answer to be correct, it has to end with I, then A. Okay. Basically, or even like if you extend it, it will also end with O, I, and A. So it's a very interesting concept if you look at it. Or now, even if you look at it in that logic, it has to end with the POIA. Yeah, no, but yeah, we'll see. So like if we traverse this one with respect to node I, let's look at this one, J. So we have J here. So its first says traverse the left and then traverse the right and then visit J. So the left, there's nothing. So let's look at traversing this right with respect to node K. So it says we have to traverse the left and then the right, which is M. So let's now pause down to the smaller subtree. So it says we have to traverse the left, which is M, to the right, which is M. And then what? So now the next one becomes M. So you see, like from B here, from B, now we're jumping to what? To M. And then from there, of course, we are now closing that, we go back to L. And then from L, before we reach K, we have to like first visit, the right of K. So we get what? M, and then we close K. Okay. And then after closing K, then we can then visit J. Okay. So now we are done visiting the left of I. Now we can visit the right of I. You see? So if we get to visit the right of I, basically, the fact that this the fact that these two have no left branches, basically like it says, when you reach O, it has no left, so you should traverse the right. But P, O, it's a leaf, so then this is a dead end. So we first put P there, and then now when we close, then we can now visit O. Now that the left and the right have all been visited, then we can now visit I. And now that this one and this one have all been visited, then we can finally visit what? A. Okay. Any questions? The time is the time is up. So just like how we can.
So are they like hybrid traversals where you have like a mixture of like one or two or all of them?
Like yeah, like depending on like how an interviewer can like can make you, maybe they're like at a certain depth, it does like some things, vice versa. But if you already know how to like follow along with the algorithms, then the other one is just a matter of them like just twisting things a little bit to make it interesting and exciting. But understanding at least this is how you follow this post order with the pre-order and with all the other ones, then it just becomes simpler. So depending, but they're on like interviewers, they can they can make it a little bit interesting. But it's not as scary also. Okay. Any questions? Okay. So let's say if you want to define maybe like a pre-order, which takes in the root, you give it the root of a tree. Okay. So what it does, for example, let's say by visiting, you perform an action like printing. So you can, for example, check, first you have to check, if the root, if the root is there, like, so for print, wait, which one is this one? Okay, let me see. Which one did you start with? Or pre-order? A print, okay, actually, pre-order, that was true. Okay. So if root, what can we do? We want to, our algorithm said, we visit the root, then we traverse the left and we traverse the right. So we can like, let's say let's assume that we have our class, okay. Okay. Now it's called, let me use a different path. Okay. Let's say you already have a class, which has to represent a node. Okay. And then we can like maybe like initialize this init where it can have maybe like some self and and data. Okay, so what we can make, like, let's say we can then say self dot left, we can like just initialize it to none in this case. And then solve dot right is equal to none, or to none, and then solve dot, maybe let's say solve dot value is equal to date. Okay, so now this represents an individual node, in a binary tree. This is a class. So now, maybe now let's say if that node is, for example, then the root, and you want to do a pre-order. So what you do basically is, for pre-order, we first have to visit the root, okay, and then traverse the left and traverse the right. So when we say that, basically we say, you print, what do you want to print? You want to print the root dot what? Dot value. Okay. And then after that, you want what? You want to call pre-order. This is the most easiest thing, we do the left and then the right. But we know that a root is a node, so it has a left and it has a right. So then you call pre-order on root dot pre-order on root dot left. Okay, and then pre-order on root dot right. Okay, that's it. So that's even the same for if you are defining in order, and then you get the root. I'll just write faster because I'm running out of battery. So basically for this one, it says you have to start in order. You start with that. So what your code will mostly be similar, but the only thing which will be, is the order of. Okay, I think I'm out of power, but yeah, basically, yeah, you can say from here that as this continues, you are just changing the order. For example, yeah, in this case, we started by by printing the root, but the first thing is like we just start by calling in order. So it is a recursive function. We call in order, and then we print, and then we call in order. In order on the left, we print in order on the right. And then even with the post order, we start by calling post order on the left, post order on the right, and then we print. So by just changing, like, how the, so look at the first example. Yeah, for this one for pre-order. And then from there we can draw how the second example should be, and also how the third example should be. Any questions? My thing is at 1%, and I think we might be, yeah, we might, yeah, it's almost 2 hours has ended. Okay, no questions for now. So
sorry, I have just a small question. Like, I'm not sure if you mentioned this because in BLH, but like, where is this like used?
oh,
This
wait.
thing, a binary tree, like, where is it used? Like, with applications, I guess.
Oh, okay. Let me think. So maybe let me try to think of so the first one, like, it's just like for searching, like if you're searching through if you're searching through like some elements, because of this property of of a binary search tree, that by like searching through or going through like one with like the ways in which you can search them, you can like search them at a much faster pace. So let me just Google some properties because that answer is not good. Yeah, they're straight up in my word. Application of binary search of binary tree. Okay, on Stack Overflow, yeah, binary search tree. Yeah, so wait. So the thing is, you can also these are binary trees. You can use them in binary search trees, where you know that like you have like data which is like entering or leaving, and then for they are also used for it says for in binary space partition, like people are doing like rendering for like 3D yeah video games or stuff like that. But then one example which I used when I was I think my sophomore year or my freshman year at Berkeley, where I was taking a class on data structures and algorithms. So we wanted to visualize wanted to build a small version of Google Maps for the city of Berkeley. Okay, so now we wanted a way, to raster the images. For example, if you open Google Maps, you can basically like see, how you can see how someone. Okay, let me stop recording and then like share something with my screen. Okay. Okay, I don't know where Zoom is. Okay. Now I can't find Zoom, so I'll just explain. So if with so every time when you zoom, like if you open Google Maps right now, it does as like, oh, you can see there is like maybe the whole earth. But if you're looking at the whole earth, you can't see some buildings. You can't see, for example, your Stanford buildings, or you can't see maybe some other, even like, geographical landmarks. Like if you are zooming over Zimbabwe, you can't see, you can like, oh, there's Victoria Falls, but you can't see, or there's the NRSH building or so. But then as you start zooming in, now you start seeing new information, okay, being produced. So for us in that case, what we're doing is we decided to extend this idea of a binary tree. Instead of it just having a left and right, for us it had like 4 children to kind of represent the tiles of the data which you wanted to store. So each node then will store information like the picture for that particular tile. So now when we would want to do traversals, for example, maybe we want to get all the nodes which had one level. Okay, because by zooming, for example, if you are zooming, you can think of the root node as representing the first picture. And then now the other nodes, which are children to that node, they are now representing a more, detailed picture. So we used those, like we stored information data in those nodes. Based on how you stored the information, like, in that value field, you can even store so much information within the node because it's like just adding to like attributes of the class. And also how you want to use that information, then traversing the graph in this way might be a good idea. So now, we have the pre-order, the in-order, and the post-order, but there are also some other like graph traversals, like the depth first search, the breadth first search, you have like all this, like the A-star, all these algorithms. So mostly they kind of like how Google Maps, like if you want to leave one location and go to another, it also has to do some kind of of traversal. So a tree is a simplified version, for example, of a graph. So, but yeah, as you expand more knowledge, you can like just, if you want to learn more on this, you can just look more on like doing traversals for graphs. But that's a good question. And I can't find my Zoom. Okay, yeah, my Zoom is there. So any questions? Proud, did I answer your? Okay. Oh, yeah, no, I couldn't see the chat, so I kept on talking. But